In this sequence, we are going to show you how to configure your computer before you actually start configuring the SIMATIC PCS 7 application. This step has to be carried out once at the beginning of the configuration phase. It is basically required to define the communication links between the automation components and to create the project itself. In the first step, the computer will be configured for communication. Let's assume that the SIMATIC Net hardware has been configured with the help of the SIMATIC Net commissioning wizard. An Ethernet adapter that is integrated in the computer mainboard is used for communication with the automation system. Now start the Station Configuration Editor. In the Station Configuration Editor, the required applications and hardware components are inserted in the table and parameterized if required. A WinCC application is inserted. The objects can be entered at any position or index in the table. However, the indexes selected here should match the configuration of the computer, which will be carried out in the SIMATIC Manager. The Ethernet adapter has already been configured with the help of the commissioning wizard in Index 5. The computer configuration is now completed. The PCS7 New Project wizard allows you to create a new PCS7 multi-project with just a few clicks of the mouse. The wizard is now opened. The project is defined and created in only 4 steps. Multi-project with project and master data library has been pre-selected. In the second step, the automation system hardware is selected. A CPU 416-2 is used here. In the third step, the number of levels in the plant hierarchy is first selected. The plant hierarchy is a representation of your plant structure within the engineering system. You can select up to 5 levels, depending on the structure and complexity of your plant. In our example, we are using 3 levels. Because the application will include both CFCs, which are used for process control, and SFCs, which are used for sequential control, both options are activated. A standalone operator station architecture is selected. In the fourth and last step, the name and location of the project are defined. The project name is FAST-E. The suggested location will be used. The rest of the work is done in 2 views, Component View and Plant View. The Process Object View is started if it is required. The views are arranged one on top of the other. With the help of the wizard, the multi-project FAST-E MP has been created with a SIMATIC S7400 station, a SIMATIC PC station, and a master data library FAST-E Lib. The new multi-project is shown in the 2 selected views in the SIMATIC Manager. In this sequence, we are going to show you how the names of the components can be adapted to the specifications of your plant. We will set up the hardware configuration of the S7400 automation system and the ET200M distributed I/O system, along with defining the symbolic addressing of the signals for the individual input-output modules. In the new multi-project, the wizard has created a SIMATIC station, which will now be configured in the component view. First, the name of the PC station is adapted to the name of the PC. This helps to simplify engineering in distributed automation solutions with several OS servers. Now the computer is configured with HWconfig. This integrated part of PCS7 allows you to configure PC stations and automation systems. The configuration is carried out according to the previous basic PC configuration in what we call the Station Configuration Editor. A WinCC application has already been inserted in Index 1. The Ethernet adapter is inserted in Index 5. The address is entered in the Ethernet adapter properties. Finally, the adapter is assigned to a network. The configuration is now completed. It is compiled and downloaded. HWConfig is now closed. In the new multi-project, the wizard has automatically created an automation station, which should be renamed in the component view so that it can be better identified. Next, the system hardware configuration and layout is performed. First, the S7400 station is renamed so that it can be identified better in AS1. It's recommended to name the controller after the process areas it is to be used to control. The name of the S7 program is adapted to the AS name. Now the automation system is configured. In the first step, we check whether the preset hardware components in the wizard match the actual components. First, the rack is checked. The part number matches the actual hardware. Now the power supply is checked. The part numbers don't match. For this reason, those part numbers are replaced by those of the actual modules used in the system. The configured CPU matches the actual component. Next, a communications processor, CP443-1, is inserted for Ethernet communication. Now, various settings are defined in the Properties dialog. First, the ISO protocol is activated, and the MAC address is entered. The IP protocol is not used. For this reason, it is deactivated. Finally, the communications processor is assigned to the system bus network. The CP443-5 extended is configured for access to the Profibus. Again, some adjustments are made in the Properties dialog. The first step is to create a new Profibus string, which will have the name DP1. The last step is to open the Properties dialog with the right mouse button and to set the CP operating mode to DP Master. The S7416 automation system hardware is now fully configured and has been assigned to the system bus network. An ET200M distributed I/O system with an address of 3 is connected to the Profibus DP segment called DP1. It will be configured in the next step. In the first step, the IM153-2 is added to the Profibus string DP1. The address is set to 3. The ET200M is equipped with an analog input, an analog output, a digital input, and a digital output, which will all be configured. The analog input module is plugged into slot 4. This module is included in the catalog of hardware that is optimized for use with PCS7 v60. The analog output module is plugged into slot 5. This module is included in the standard hardware catalog. In this profile, you can find all modules that are supported by and are compatible with SIMATIC PCS 7. However, we recommend that you work with the PCS7 v60 catalog, since it contains the subset of available hardware modules that are optimized for use with PCS7 v60, and therefore enables you to work more efficiently. The digital input module is included in the PCS7 v60 catalog. It is plugged into slot 6. The last module to be configured is the digital output module in slot 7. In the hardware configuration, the IM153-2 interface for the ET200M distributed I/O system was inserted into the rack and communication was set up. The ET200M rack was expanded with analog and digital input-output modules based on the hardware that is to be used on the project. In order to use symbolic addressing of I/O throughout the configuration, instead of rack slot channel numbers or memory locations, each address is given a unique symbolical name and comment in the Edit Symbols dialog. The Edit Symbols dialog is activated to enter the symbols. The symbol name PVIN of controller 1 is entered in the first line as well as in the comment column. This is done by copying the symbol name to the clipboard and pasting it into the comment field. The corresponding symbol name of controller 2 is entered in the second line as well as in the comment column. The corresponding symbol name of the current value of the manipulated variable controller 1 is entered in the third line as well as in the comment column. The corresponding symbol name of controller 2 is entered in the fourth line as well as in the comment column. The dialog is completed by clicking OK. The symbolic names of the analog input signals have been defined and assigned to the channels of the module. Next, the symbolic addressing of the analog output module's channels will be assigned. Again, the Edit Symbols dialog is opened for entering the symbols. The symbol name of the controller 2 output is entered in the first line as well as in the comment column. The corresponding output of controller 2 is entered in the second line as well as in the comment column. The dialog is completed by clicking OK. Symbolic names have now been assigned to the channels of the analog output module. The symbolic addresses of the digital input module are assigned in the same manner. Again, the Edit Symbols dialog is opened. The symbol name of the feedback signal ON of motor 1 is entered in the first line as well as in the comment column. The corresponding symbol name of motor 2 is entered in the second line as well as in the comment column. The symbol name of feedback signal OPEN of valve 1 is entered in the third line as well as in the comment column. The symbol name of feedback signal closed of valve 1 is entered in the fourth line as well as in the comment column. The symbol name of feedback signal open of valve 2 is entered in the fifth line as well as in the comment column. The symbol name of feedback signal closed of valve 2 is entered in the sixth line as well as in the comment column. The dialog is completed by clicking OK. Symbol name has now been completed for the digital input module. The last step is to assign the symbolic addresses to the channels of the digital output module. The Edit Symbols dialog is again opened. The symbol name for switching motor 1 on-off is entered in both the first line as well as in the comment column. The corresponding name for motor 2 is entered in both the second line as well as in the comment column. The symbol name for opening or closing valve 1 is entered in the third line as well as in the comment column. The corresponding name for valve 2 is entered in the fourth line as well as in the comment column. The dialog is completed by clicking OK. The assignment of the symbolic names for the channels of the digital output module has been completed. All of the required symbolic addressing has been defined. In later configuration steps, you will be able to easily make use of these symbolic names without having to reference physical addresses. A named connection is set up to ensure reliable communication between the operator station and the automation system. It is configured from the NetPro interface. NetPro is started. In order to define the named connection, the WinCC application is first selected in the SIMATIC station. All existing connections are displayed in this table. A new connection is created by double-clicking on an empty cell. This is the CPU to which we want to define the connection. In the Properties dialog, the name of the connection is changed to OS1 AS1. No further information is required. Now the changes must be saved and compiled. The compilation has been carried out without errors. Now the hardware configuration and the named connection are loaded into the AS. The AS is selected with the left mouse button and is then loaded. the CPU is again set to Run status. In the last step, the named connection is loaded into the SIMATIC station. The WinCC application is selected and the connection is loaded. NetPro and HWConfig are terminated. The hardware-specific part of the configuration example is now finished. You are now ready to begin configuration of the actual application program. In this sequence, we're going to show you how you can implement your own templates, that is, sample solutions for specific process automation functions, in SIMATIC PCS 7, as a basis for carrying out the application engineering of your plant. In addition to these sample solutions, which are created in the form of CFC charts, a sequential control program in the form of an SFC chart is also used. The SIMATIC PCS 7 library comes with standard templates, for example for motors, valves, and controllers. For the purposes of this exercise, we will make use of a customized library to show you how you can use your own company-specific templates. In the following steps, this library will be de-archived using the SIMATIC Manager. The individual CFC charts will be copied into the master data library. Copying is carried out between the library in the component view and the charts directory of the S7 program in the master data library. To de-archive the library, the menu command File De-archive must be carried out. In the De-archive Select Archive dialog, the archive file symlib.en-zip is selected and opened. In the Select Target Directory dialog, the FAST-E folder is selected in which the project was stored. Since the charts contained in the library must be added to the project, we acknowledge with Yes to open the library. The three plans, Motor 1, Valve 1, and PID Control 1, are copied into the master data library. With the Control button pressed, the charts are selected one by one and copied into the Charts folder in the master data library. The charts are now available to be used throughout the project. The SimLib can now be closed. In the master data library, sample charts, functions blocks, measuring points, and higher-level engineered solutions are stored, so that they will be available for use in the entire project. The three CFC charts now have to be copied from the master data library FAST-E-lib into the FAST-E-PRJ project in the Function 1 folder of the system. Once the CFC plans have been copied, it is possible to carry out further configuration steps. The following tasks will be carried out in the Process Object view in the SIMATIC Manager. This view guarantees a uniform and comprehensive look into all important aspects of the complete automation solution. Many changes can be made here directly, without having to start the individual editing tools. Filter functions allow the number of displayed objects to be reduced in such a manner that only those objects are displayed that are required for the task at hand. In addition, an undo-redo function is also available. The three charts are displayed in the FAST-E-lib library in the Templates folder. All three charts are now copied into the Function 1 folder. The charts are selected and copied into this folder using drag and drop with the left mouse button pressed. The charts are now available in the project. In our example, there are two identical process areas or units in the plant. Automation of both of the units must be carried out in such a manner that one unit is fully engineered first and tested prior to beginning configuration of the second unit. The automation programs of the first unit are then copied and adapted to the second unit. Before the CFC charts are interconnected, an SFC chart must be created to control the sequential operation of the motor and valve, since this configuration logic must also be available for the second plant section. The SFC plan SFC1 created by the PCS7 wizard in the Function1 folder of the FAST-EPRJ project is renamed and adapted for the simulation. In the first step, the SFC plan SFC1 that was created by the project wizard is renamed to Control. The object SFC1 in the Function1 folder is selected with the right mouse button, and Object Properties is called up from the context menu of Operations. The engineering of the sequence of operations is carried out in the SFC editor. A step and its associated transition are now inserted. All of the required steps and transitions have now been entered. Before configuring the commands and transition criteria in the steps and transitions, the cursor must be set to selection mode. In the first transition, a condition must be entered which leads to a transition to the next step. The object properties of Transition 2 are selected in the context menu. First, a comment is entered. The Condition tab is selected to enter the condition. The PV-in variable of the PID module in the PID Control 1 chart, which is to be used in the transition, is searched for by clicking on the Browse button. The transition must take place if this variable reaches a value greater than or equal to 50. The condition for this transition has now been inserted. The dialog can now be closed. Next, the commands for the subsequent step will be defined. The entries will again be made in the object properties. For clarity, the name is changed to Motor On. The minimal duration for execution of the step will be set to 10 seconds. It is entered in the Minimal Durations field. The Processing tab is selected to enter the commands which are to be executed during the step. The Auto On variable of the motor function block, which is contained in the Motor 1 chart, is located. The value that is to be written is true. This is done by entering the number 1. The motor is switched on if the process value PV-in goes above 50. After 10 seconds, the motor should be switched off again. The Motor On step and transition are copied. This is done by opening the context menu and selecting the Copy command. The sequence is pasted in the chart using the Insert command from the context menu. The object properties of the inserted Motor On sequence are selected. First, the name is changed to Motor Off. The Switch Off command is triggered. This is done by writing the value 0 instead of 1 to the Auto On variable of the motor module. The sequence of operations is now defined, and the SFC editor is closed. The sequence of operations called Control switches the motor 1, on as soon as the process value PV-in goes above 50. After 10 seconds, the motor is switched off again. This is a very simple application to illustrate the power and ease of use of the SFC editor. Real sequential control operations can be far more complex. For example, it is typically recommended to include an evaluation of the feedback signals within the transition conditions. The next step is to modify the default naming conventions that were automatically applied by the system, and to delete objects that were created by the system but that are not required in this example. The first step is to rename the Process Cell 1 folder to Process Cell. The Process Cell 1 folder is selected with the right mouse button, and Rename is called up from the context-sensitive menu. Now the Unit 1 folder is renamed Unit A. The CFC plan CFC1 that was created automatically by the project wizard is not needed, and thus can be deleted. In this sequence, we're going to show you how SIMATIC PCS 7 automatically populates process graphics with symbols which are pre-linked to function blocks in the controller configuration. Based on the controller configuration, PCS7 can automatically create symbols which allow the operator to control and monitor CFC and SFC charts from process pictures. These block symbols are automatically linked to their associated faceplates. Generation of these block symbols and the process for linking a symbol to a faceplate can be executed on demand. However, this function is often selected and carried out during compilation of the operator station. Some preparations have to be made for the block symbols to be created automatically. Because it is not always desirable that faceplates are automatically generated, this function must be explicitly selected for each process graphic. In this example, the function will be selected for Picture 3 in the Unit A folder. The properties of Picture 3 are selected. The function is selected in the Block Symbols tab. Now, the option Derive Block Symbols from the Plant Hierarchy is activated. The dialog is closed. With PCS7, it is possible to create a process graphic hierarchy in the OS for operator navigation, which matches the plant hierarchy configured in the controller. The top level in the picture tree hierarchy must correspond to level 2 in the plant hierarchy. The Plant Hierarchy Settings dialog is opened. To determine if the system is set up to automatically generate a hierarchical picture tree, the level 2 of the plant hierarchy must be selected. The setting to derive the picture hierarchy from the plant hierarchy has already been selected. The settings are now completed. With these settings, SIMATIC PCS7 will automatically generate all block symbols, create them in the corresponding pictures, and connect them with their associated faceplates when the operator station is compiled. In this sequence, we're going to show you how you can efficiently and easily create an exact copy of a pre-existing unit. As already pointed out earlier, 2 identical units with identical instrumentation are used in this project. Automation of Unit B is simply carried out by copying Unit A and modifying the instance names. It is not necessary to modify the actual programs, that is, to change the CFC and SFC charts. This is exactly what helps you to save engineering time, to avoid errors, and to minimize the validation and checkout time. All aspects of Unit A are copied to the clipboard in a single operation, and then pasted into the Process Cell folder. The copy of Unit A is named Unit A1. It will now be renamed Unit B. Now the names of the CFC and SFC charts contained within the duplicated unit are renamed. The contents of the Function 1 folder in Unit B are displayed. Motor 1 is renamed Motor 2. The PID Control 1 chart is renamed PID Control 2. Likewise, the Valve 1 chart is renamed Valve 2. The property that block symbols are to be automatically created within the process graphics or pictures in Unit B has been copied as well. This is all it takes. Unit B has been configured by cloning Unit A. Are you already familiar with the Import-Export wizard? With the help of this powerful tool, you can automatically create any number of copies of standard or project-specific elements, such as CFC charts, SFCs, function blocks, or entire process areas. It is also possible to adjust instance-specific parameters, attributes, and signals to take into account each individual instance. In this sequence, we are going to show you how you can easily assign I/O signals to the individual charts and function blocks that are used in the application. We will use the symbolical names which have been defined previously, and assign them to the corresponding measuring points. The signals are interfaced easily and conveniently in the Process Object view. In this view, it is possible to carry out all assignments globally, without having to open up each individual chart or function block one by one. The next thing to do is to insert the signals. and then to modify the parameter values. The signals are entered one after another. The first entry will be for the feedback signal ON of motor 1. With the right mouse button, the input field in the signal column and in the motor 1 line is selected. Then the Insert Signal command is triggered. In the Insert Signal window, all of the defined signals are displayed. They are sorted according to input and output. The signal names contain the name of the measuring point, the chart column, and the name of the channel drivers in the module column. The signal that is to be inserted is motor 1 FB on. It is selected and will be applied by clicking the Apply button. The other signals are connected in the same manner. For the Start-Stop command signal of motor 1. For the feedback signal of motor 2. For the command signal of motor 2. For the position feedback signal of the output of controller 1. For the output signal of controller 1. For the process variable of controller 1. For the position feedback signal of the output of controller 2. For the output signal of controller 2. And for the process variable of controller 2. Finally, the I/O signals for valve 1 and valve 2 are connected. For the closed feedback signal of valve 1. For the open feedback signal of valve 1. For the open-close command signal of valve 1. For the closed feedback signal of valve 2. For the open feedback signal of valve 2. For the open-close command signal of valve 2. All signals are now interconnected. The dialog may now be closed. Now, the monitoring time parameter of the valve modules in the valve 1 and valve 2 plans will be changed from 5 to 6 seconds. These changes are carried out in the Parameter tab. For clarity, we will split the window again to display the chart column in the left section and the measuring point connection, category, and value columns in the right section. Now we can enter the value 6. To change the monitoring time of valve 2, we select the input field in the left section of the Process Object View valve 2 and enter the value. The interconnections and parameter changes that were carried out in the Process Object View have been applied to the plans. The valve 2 plan is opened to illustrate this. The interconnections of the feedback signals are visible here, and those of the output for commanding the valve to open or close are visible here. The modification to the monitoring time has been applied as well. The application engineering of our example project is now completed. In this sequence, we're going to show you how you can compile the application program and load it into the corresponding components, easily and via a central dialog. Let's again summarize the steps we have taken so far. Engineering of the application example is completed. All default settings for deriving the process graphic navigation hierarchy and for generating the faceplates have been defined. The operator station can now be compiled, and the automation system program can be compiled and loaded. In the Compile and Load Objects dialog in the SIMATIC Manager, all required settings for compiling and downloading the plans and the operator station can be defined. With the right mouse button, the top hierarchy folder FastEPRJ in the left window is marked. Then the command for compiling and downloading Compile and Download Objects is selected in the context menu. For the Charts folder, the option boxes in the Compile and Download columns are activated. The options settings for compiling and downloading the AS program are carried out in the Compile Program Download to Target System dialog. Compilation of the entire program is set here. The module drivers will also be generated. The sampling times will be automatically updated. If modifications are made later, the setting is defined such that the option for compiling and downloading changes only is available. The download settings are defined in the S7 Download tab. The entire program will be loaded. This dialog is confirmed. For the OS1, compile is loaded. Since no OS servers with clients are implemented, download of OS1 will not be selected. The options for compilation and download of the OS program are also defined in the Compile Program Download to Target System dialog. This dialog is launched by clicking the Processing button. The AS1 Prog AS program has already been assigned to OS1. Communication via the configured named connection has been predefined as well. In this dialog, the following options are activated. Tags and messages, for compilation of tags and messages. SFC visualization, for automatic creation of displays for monitoring and interacting with SFCs. Picture tree, for creating the image hierarchy from the plant hierarchy. Block icons will additionally be created or updated. In the first compilation procedure, entire OS will be selected with memory reset. The selection is applied. This warning may be acknowledged. Now we can start compiling and downloading. This dialog can be acknowledged with OK as well. The log and the operator station is ready to start. In the operator station, all faceplates have been generated and the picture hierarchy has been created. The compile and download dialog may now be closed. The configuration phase is now completed, and we can start testing and commissioning. In this last sequence, we are going to show you, based on the configuration steps that we have carried out, how the example project can be used by an operator to monitor and control the process. The process object view is now closed, and the OS project is opened and activated. With the right mouse button, OS1 is selected, and the Open command is triggered in the context menu. The project is activated in the WinCC Explorer. Now, Unit A is selected. All symbols contained in the picture were automatically generated. They can be rearranged using the graphics designer. The pictures may, for example, also be supplemented with static graphical elements. The HMI is communicating with the controller configuration in the AS. By clicking on the block symbol for motor 1, the motor's faceplate is launched. The first thing to do is to reset the motor module in the AS. Now the motor is started. The motor start is displayed in the status. The motor is stopped. The motor is now set to auto mode. The faceplates of the controller and the valve are also selected by clicking on their block symbols. The controller must be set to auto mode. The setpoint value is now set to 40. Now, a display for monitoring and controlling the SFC will be called up. This is done by changing the key set and clicking on the SFC visualization button. The SFC is selected. The SFC overview is now displayed. The detail view is selected by clicking on the SFC control. The sequence is now started. Since the actual value of the process variable is not greater than 50, there will be no transition. This set point is now changed to 90, causing the process variable to increase. It is entered in the faceplate of PID Control 1. The sequence will now run through to completion. Motor 1 will be started in the third step of the sequence and be switched off again in step 4, after the configured step duration time of 10 seconds has elapsed. Key set 1 is again selected to display alarm and operations lists, and the alarm system is selected. A list of the incoming alarm messages is now displayed in the workspace. The